ശരി. അപ്പം അച്ഛൻ
Hello, audible? Hello, audible?
Yes, sir. Audible.
Yes, sir. Great, great. Thank you very much. Let us now we start. Hello, Dilip, please host me. Here we take a transformer questions, okay, today. Okay, this is your all the question papers.
Sir, your screen is not sharing, sir.
Just I will share, okay, not issue. क्या चला गया बंदा Very teacher. Yeah, okay. No, okay. Transformer. Yeah. This is another page set of questions. Here we also copy October month question paper. No? question along with this, add with delta star basic equation. Okay, this complete question if we take. Fifth question. So here, this is one question is asked in your exam, easy or written. Okay. It is here, it is asked in your ETO exam in October month. Okay. October 2020. Yeah. With an add of star delta connection diagram, state the basic equation from which star delta or delta star conversion equation can be derived. So he is not asked to you drive the star delta conversion equation. No, that basic. Okay. So this part A of this question, fifth, when we solve this, answer fifth A. Just you drive three-phase connections or polyphase connections. Either we connect first is balanced star three-phase star connection, star connection. Second is balance delta. Second is balance three-phase delta. Balance means in each phase same impedance. Okay. So let us like a three-phase induction motor or three-phase transformer winding is balanced. Okay. So let's say star connection. So here is the impedance we can write here. Like this impedance has a resistance and reactance combination. Okay. Or we can easily put with you show like this is your per phase impedance. Okay, either you solve with the load side or this supply side means you can show the winding. Okay, so this is your load impedance per phase. Okay, suppose this is your star connection. Okay, dear. So this is like R, Y, B each phase. This is the phase impedance per phase. Phase impedance. equal ZPH, phase per phase impedance. Okay, Z. Okay. Now here this is the line current. So here it is a phase current. Then this is the neutral point. So between this neutral and any line, that is called as a phase voltage. The voltage across phase winding or phase impedance. But the voltage between any two phases, that is called line voltage. So for balanced three-phase delta connection, what is the basic equation? Your this phase voltage, line voltage equals to √3 times of phase voltage. But here line current equals to phase current for delta. But for star, this is your delta connection for delta. This is your per phase impedance. Now same impedance if we connect with this is the delta connected load, balanced delta. Here is RYB three phase, where it is a three phase supply, okay, three phase. Then this is the per phase, impedance, equal impedance, Z. Is not required to write this. Here also it is not required. Z are equal here, okay. And it is per phase only, okay. Now, again the voltage across two lines, two phases, that is line voltage. Now voltage across each phase winding, this Z impedance, it is here V phase. Here it is V phase. Here. Now if we measure potential here or here, it is same. So this is equal actually. This is Z. But current, if we talk about current, here it is a line current. But when it is come here, it is divide like, okay, here and here. Sorry, this is this. So this is the phase current. Okay, this is the phase current. Correct. So for this delta, your line current equals to √3 times of phase current. Phase current. And line voltage equals to phase voltage, but okay. So these are the equation are used for this, okay. From this we can convert the star to delta or delta to star. Now second question was, there is a part B, fifth part B. Here it is given 230 by 115 volt single phase transformer. So it is supply at load, at load condition. Load means, or it is, there is a load current. Load current means secondary side current. It is a 5 ampere. 8, it is 0.86 lagging power factor. Okay, dear, power factor, lagging power factor. Okay, means cos phi 2 is 0.86, then phi 2 cos inverse of 0.86. Then it comes how much actually? Please, you look with the calculator. What is the value? Cos shift inverse, it is 0.86. Then its angle comes 30. This angle comes 30.68 degree. Okay. Okay. Now we this phi 2 is your phi 2. Now we can calculate a sin phi 2. Sine of this angle. Sine answer we get a 0.51. 51. Okay. Now, but at now is at lagging. The no load current, no load condition is also given. Hello. At no load and at no load. You know, no load. Cos phi naught, no load power factor. No, see first. What is the no load current? 0.2 ampere, 0.208. So this is at load condition, at no load current, that is 0.2 ampere. At cos phi naught, no load power factor is 0.208. Then phi naught we can calculate cos inverse. Yes, please. It comes 7799 means 78 degree almost. Okay, 77.99 means 78 degree. Okay, and then you can calculate sine phi naught also. So sine of this angle is 0.9978. Okay. Okay.
सर
Now
ऊपर
yeah.
फिर ऊपर वाला एट लोड कंडीशन है ना?
हाँ, this is at low. हाँ, yes. On load होना चाहिए. Okay, at load. Yeah, this is at no load. This is at load. Or at full load we can say. At load or at no load. Okay, please, yes. So these are the parameters are given. Now we can draw the phasor. Now he is asking primary current and primary power factor. So as I told now, suppose this is your vertical axis, and this is we consider as a horizontal axis. So suppose this is your V1 is the voltage, supply voltage, rated volt. That is, it is given, 230 volt. Okay, V1. Hello, V1 is given, correct? Then now turn ratio, we can calculate transformer turn ratio. K equals to V2 by V1. V2 by V1. That is 115 by 230. This value comes 0.5. Now you know for practical this is I2 dash by I2 equals to K. Then I2 dash equals to KI2. At load condition, this KI2 will be, what is the value? 5 into 0.5, correct? KI2. So this I2 dash becomes 2.5. Okay, dear. So actually, you know, now no load condition, what is the current? 0.2. At how much degree? 78 degree. So actually your no load current, it is lag with this voltage at lagging power factor V1 primary side, na? Hello, at no load, you are like, this is your transformer, my dear, okay? Here you apply V1, V1 means 230 volt, okay, 230 volt. Then there is, and this is your secondary side we kept open. So this transformer take only I naught, but at power factor is 0.208, okay? So this current is lag because this transformer is at lagging power factor very low. So your low no load current is this. This is I naught. Now you know this this is your phi naught. Phi naught means 78 degree. Now it has a two component. One is here, another is here. Okay, dear. This and this. Okay. Hello. It has a two component. This and this. Okay, dear. This is I mu. This is I W. It is I naught cos phi naught. This is I naught sin phi naught. Okay, now this current is produced. It is a magnetizing current. Now it produces the flux. It generates a flux here. Phi. Magnetizing flux. Then it induces the EMF in primary and secondary. Okay, so this is your no load voltage. It is suppose E1, it is E2. Okay. Hello, my dear. This is E1 here. Okay, E1. Here it is E2. Now you know we neglect the here voltage drop. Then B1 equals to E1. It is but negative. B1 here. Okay. It is. And this is your V2. Now suppose. Now, my dear, hello, here we put a load, suppose, on load condition. Okay, if we connect load of power factor cos phi 2 is 0.86, my dear, lagging. Okay, dear. Then this is the I2, is 5 ampere, my dear. Okay, now corresponding to this, there will be a I1. And then there is a overload power factor also, cos phi 1. This is asking this I1 and cos phi 1. So now if we put the load on secondary side, so it lag the secondary voltage at lagging power factor. Hello, if this power factor, load power factor is lagging 806, no? So it is lag, means lag the secondary voltage with angle 30 degree. This phi 2. Okay, this is your I2. Now as refer to primary side. Okay, this will come I2 dash equals to KI2, which we have calculated. It is 2.5. This is 5 ampere. Now this is magnitude is also given, point 2. This is 0.2. Now vector sum of these two current, vector sum, sorry. Vector sum is the calculate of these two. This is like this, no? So here we get, we take a red, sorry, this is your primary current I1. Now primary voltage, primary current. This is your power factor phi 1, primary power factor angle. Okay. But my dear, these two values we have. But how we calculate this I1 and cos phi 1? Okay. So as a you an engineer, you have to learn mechanics, applied mechanics, forces. Suppose vector. Suppose you have a two vector, P and Q vector. Okay, two vector P and Q. Now if we have angle between them, theta or theta, then their resultant, how we calculate their resultant R. This is the resultant R of this two vectors. Okay, this R, how we calculate? It is very simple. We calculate R square equals to P square plus Q square plus twice PQ cos theta. But my dear, then same way we can calculate. But here there is no angle available between I2 dash and I naught. This angle we not have. Okay. Then this formula we cannot use. Then another method to calculate a vector sum. Suppose you have a number of vectors are there, like at a one point a number of like. Then how we can, like it is P, Q, R vector. How we calculate their resultant, or vector sum? We resolve this vector into vertical and horizontal. Okay, we take of all vector horizontal components on this axis and vertical component on this axis. Okay, like this. Got it? So this their total vertical component, horizontal component. After you getting total vertical, total horizontal component, then we can easily calculate by Pythagoras theorem like this. This will be your resultant of total horizontal component. Okay. So this is x y, this is x total component. R we can calculate. Now R square equals to x square plus y square. Okay. And this will be your angle phi. Then we can calculate cos phi also we can calculate. So this will be used. Okay. So here first, like already we know the two component, here you write two component of I node, no load current. There is a two component. First is along x-axis. Actually, this is your x-axis, This is your x-axis, this is y-axis, okay? So this two component, how we can calculate? I note as a on along x-axis we have a I naught sine phi naught. You know, it is 0.2 into sine, what is the value? What was the value sine phi naught? Sine phi naught is this, no? Into,
0.978.
very good. And I naught cos phi naught is 0.2 into 0.208. What these two values? 0.19. Okay. And this is come 0.0416 ampere. Okay, like this. Same like we can resolve the two component of this is 2 TW2. Same like two component means horizontal and vertical. We resolve this 2 days also. Okay, I2 dash sine phi 2 and I2 dash cos phi 2. This is sine, okay. So I2 dash is 2.5. This I2 dash is 2.5, cos phi 2 dash phi 2 is 0.51. And this is 2.5 into power factor is 0.86. Okay, dear. 2.5 into 0.51. 1.275. This is 0.5 into
2.15.
great. Now it's easy. As you know, we have to calculate, along this y axis and along this x axis. So it is Ix, total component, along a total y component. So, we add this here, sine terms. This two and this two. Okay. This is along here. 0.196 plus this is your 1.275. Okay, so it comes 1.27 plus 0.196 is 1.47, and this is this we also add Ix. Ix is it comes 0.0416 plus 2.15. It comes plus 0.0416. 0.0416. Okay. 2.19 ampere. Okay, this two. Now this is the total vertical, total horizontal. Then along this axis Along this vertical axis, there is a voltage phasor is also there. V1. So now first of these two, vector sum of these two, total horizontal and total vertical, this will give you I1. This is your I1, okay? I1. This is V1. Now it means this is your phi 1. Okay. So I1, now we can calculate primary load current. Load condition. What is the primary current? I1 equals to, very simple, Ix square plus Iy square. It is 2.19 plus 1.47 whole square. Okay. For 7 square. Root answer. It comes 2.64 ampere. Okay, then primary power factor. Cos phi 1. Now in this triangle, you know.
Sorry, Ix 1.47 square, no?
1.47 square, yeah. It is square. This is Iy square. Okay, just a minute.
Sir, cos
Okay.
phi 1 phi y.
Now in this triangle, this is I1, and this is Iy, this is Ix, correct? You know this because it is parallel to this, no? So now this is a right angle. In this right angle triangle, you know, this is hypotenuse, this is theta, this is perpendicular. So you know cos equals to perpendicular means Iy
upon I1 है.
Cos is it is Iy. No, sorry.
Iy by I.
Iy
upon I1, sir.
Yeah, Iy by I1. Then it comes Iy is 2.19 divided by I1 is 2.64.
.83.
Yeah, so it is 0.83 lagging or 129 lagging power factor. Okay, so this is the overall power factor of. Very easy. Okay, so just you consider the at no load and load condition. Okay, please, if you require, you take a screenshot or whatever. Okay. Same, there was another question in ETO earlier. It is asked number of times. There was a famous question. Same kind. Let us we discuss it. Okay. It was this first question for ETO's collection. here. Here. Okay, this first from ETO set of question. Part of first question. 100 kVA 24000 by 240 volt single phase transformer. Okay. Now we said that at no load. At no load. At no load. Okay, at no load condition. Suppose this is your transformer at no load. This is your primary side. Okay. Here you apply HV side. It is 2400. And the secondary side, suppose it is kept open. Then this transformer take here I naught only. Okay. So what is the at no load? It is given. Then no load power input. It is given. Okay. And core loss. You know, core loss. We measure, you know, in open circuit test, we measure this power input. No load power input equals to total core loss. Okay. So core loss were given 700 watt. So let us, and you know, no load input power is considered as a core loss. Okay, core loss. That is W naught. That is given 700 watt. No load input W naught equals to V1 I naught cos phi naught. No load power factor this. Now from and this equals to core loss for iron loss. Okay, so it means therefore we can calculate now. Now this no load current I naught is given 0.64 ampere. The no load current. Then no load power input from this. Now we can calculate no load power factor. That is W naught by V1 I naught. My dear, this is 700 divided by 2400 into 64. This is the current. Please. From this we can calculate the power factor. Just a minute, please.
Point 45. 55.
Hello. Hello. Sorry. Are you audible?
Yes, sir.
Okay. I think आप लोगों ने कैलकुलेट किया होगा. What is the value, please?
0.456.
0.455, sir. 0.455.
Okay. So let us say it is okay. It no. Oh, very low. No? It is 0.1866. Just a minute. 2400 into 0.64 inverse into 700. No? Oh yes, 0.45556 we can write. It is 0.456. Okay. Okay. Now we can calculate phi naught also. Okay, that is cos inverse of this 0.456. Then it comes to cos inverse answer 63.88. Then you can calculate sin phi naught also, because these all values we require. The sine of this, it is 0.89. Okay. So this is the at no load condition. Now, when we connect the load, okay, at load you can write at load. So at load condition, okay, this is your primary side. Then on secondary we put a load. Okay. So there is a load current, I2. And this is I2 is 40 ampere is given, okay, at 0.8 lagging power factor. Okay, dear, I2 is this. Okay. Now we can calculate this is cos phi 2, 0.8. Then phi 2 is, if you don't know, it comes 3686, I think. 368. 3686. Okay. Then you can calculate sin phi 2. It comes 0.6. Okay, dear. Now turn ratio also. Okay, on this now we can calculate turn ratio V2 by V1. That is 240 by 2400. So it comes 1 by 10. Then we can calculate I2 days equals to KI2. That is 40 into 1 by 10 means it is 4 ampere. No? Okay, dear. I2 days. So now other thing is same like, okay. Here now two component I naught. Two component of I naught is two component of I naught. That is I naught sin phi naught, I naught cos phi naught. Sorry. What is this values? Very simple. It is 0.64 into 0.64 into cos value is 0.4556, or this is 0.89, huh? My dear, this and this. Point 0.64 into 0.456.
Sir, 0.292.
Very good. 0.29.
Other one is a 0.569.
This is 0.569.
569.
Okay, this much. Okay. Now similarly we can calculate two component of we resolve the I2 dash also. I2 dash cos I2. Just a minute. Yes, please. Okay. So it is I2 dash cos phi 2. First we write the sign value. Okay. Sin phi 2, and this is I2 dash cos phi 2. So my dear, this is I2 dash means 4 into, cos phi 2 is 0.6.
0.6.
And this is 4 into 0.8. So 2.4 is 3.2. Now, my dear, same like you draw the vector diagram, this part, this part. Yes, no. Okay, this thing you have to like here to draw this vector diagram, same, nothing change, only values will be changed. Okay, this part is same part. Please try yourself. You draw the vector diagram, values we have. Okay, where we have here. Okay, And he is asking, see here in this question, na, hello. Actually, in this question, he is asked, see, it is divided in two parts. He said that calculate two component of no load current. So two component of no load current, you get a mark here. So this is your active sorry, this is your passive or passive component. And this is your active or loss component. This is your passive or magnetizing. So you get a marks of this, and this is denoted by I mu. This is I omega. Okay, dear. Then he is asked the primary current and primary power factor. Okay, here. Now he said that, see, you potential difference. Determine the primary voltage and primary power factor. Ignore the leakage impedance. Means here impedance drop. You have to neglect. That's why E1 was to V1. V1 and E1 are equal. V2 and E2 are equal. Okay, no drop. Okay, dear. Okay. Do I will just you do
Sir, explain one more time, sir. Yes, please. Yeah. So this is now total horizontal component means along x-axis. Okay. And total vertical means component that is along y-axis. Okay, so this is Ix equals to means sine term. Okay, so it is 0.292 plus 2.4, and here it is Iy equals to 0.5 569 plus 3.2. So this comes 0.292 plus 2.4. It comes 269. 2.69, okay? And this comes 0.569 plus 3. It comes 3.76. Okay, then we have to draw this vector diagram. Okay, like so this is your vertical axis. Okay, on vertical axis. Let us, this is you assume this is your horizontal axis. And now let us, it is your applied voltage V1. Now your no load current is lag this voltage by phi naught. Phi naught. This is I naught. Now it has a two component. This and this. This is I mu. This is I omega. Okay, dear. Now because it is a magnetizing current, then it produces a flux. Then there is an induced voltage in primary and secondary to E1. This is V1 minus beta because it is negative. And this is your V2 is equals to minus V1. Now at load, your current, load current is like this I2 is phi 2. Phi 2, okay. Now, as referred to primary side, this is your phi 2 days. Sorry, I2 days. I2 days. This is phi 2 again, okay. But now vector sum of this two current, okay. This will give you, this is your I1. Okay. Now, similarly, the I naught, we resolve this I2 days also in horizontal and vertical component. Okay. Then we calculate a total, this Ix and Iy. So like your total vertical and total horizontal. This is Ix, this is Iy. Then their vector sum. Okay. This will give you I1. Now this I1 equals to Ix square plus Iy square. Okay. Then cos phi 1 primary power factor. Current and power factor. Okay. Iy by I1. Okay. This will be your phi 1 And because along this axis your V1 is there, no? The V1, I1, this is I1, okay? This comes
4.5.
yeah, 4.63 ampere. And this will come IY is 3.769. 4.63. Point 813. 814 lagging. Okay, dear. So this type of question was asked, okay, on this. Okay. Means it was asked in October. Now November, December, it may can repeat this question. Okay. This first we have solved now, right? Hello. There is a chance this time this question will repeat.
लेकिन सर लास्ट 4-5 मंथ क्वेश्चन इज नॉट रिपीट ना सर.
रिपीट हुआ है ना, वो एक अल्टरनेटर वाले क्वेश्चन तो अभी अब रिपीट होने शुरू हो जाएंगे मोस्टली. 3-4 सेट हो गए ना. ओके, मे बी 1-2 क्वेश्चन दे रिपीट. ओके, अभी नए क्वेश्चन आएंगे 2-3 महीने बाद में, फिर उन्हीं में से रिपीटेशन शुरू हो जाएगा. ओके. Now there is a questions on losses and efficiency of transformer. Okay, like here this second question. Okay. With reference to the large electrical transformer on board, state where this transformer may be used for manpower distribution, like at a generating station and this intermediate station in transmission and distribution line. Then in power distribution at the end user, like on board. State the typical efficiency range is 97 to 99%, 98% it is. Protective devices. So it is then on dry type transformer, you know, under voltage, overload, short circuit. Then there is a, you know, temperature, continuous monitoring of winding temperature. Okay, on the scanner there is a, you know, continuous monitoring by we put the thermocouple on the windings in dry type. Okay. Maintenance requirements. What are the maintenance? In oil type there is a major maintenance, but here in dry type, you know, maintenance is primarily maintenance. We actually dust deposit is the main causes failure of dry type transformer. देखिए ऑयल टाइम में तो क्या होता है, जब मॉइस्चर अगर जाएगा, इसलिए हम सिलिका ब्रेदर यूज करते हैं ना. ओके, टू रिमूव द मॉइस्चर फ्रॉम द एयर विच इज गो इनसाइड द ऑयल टैंक ड्यूरिंग
your expansion and when load is decrease or increase. When load is fluctuate now in transformer, your level of oil in the tank is vary. That is, if overload, then heating, then it is volume is increased, it go to conservator tank. When it load is down, then it reduce the volume, then oil is flow from conservator to main tank. Then it suck the air. Okay, because वो breathing करेगा ना, अगर level up down होगा. Then this air, atmospheric air is enter. Now in air there may be impurities, maybe moisture is there. When moisture is go, it deteriorate your oil insulation. But in dry type, actually main causes of winding insulation failure is if there is a void means hole, so crack, and when it absorbs some moisture outside. Now moisture is by dust deposit. When dust is deposited on the winding, so there is you have to, in the oil dry type transformer, we have to remove the dust periodically, weekly or what is it, daily, like deposit of dust. Then we check like other parameter, what is your temperature. We continuously monitor the temperature of winding because it is directly proportional to your load or overload, or maybe then. Okay, now under voltage, short circuit, overload. These are the protection we have provided for that. So maintenance is, this is okay, please check. Now there is a part 2 is this transformer. Earlier this question was asked in number of times, this part B, but there was this is given in kilowatt, this 25, not in kVA, kilowatt. Now it is correct. Okay, because it should be in kVA, because transformer rating in kVA, and here power factor is given. Okay, just we cover this today. So before we start, the question was asked different type of losses in here, in some question this is asked. Different type of losses occurs in a transformer. So we discussed the losses and efficiency of transformer. अभी actually हमने वो cover नहीं किया है ना, losses and efficiency. Okay. Losses and efficiency of okay. Major loss in transformer are, first we categorize as a copper loss, that is called as a variable loss also, total copper loss. This copper losses are copper loss. This is due to this is due to resistance of primary and secondary winding resistance. So that total copper loss is I1 square R1 plus I2 square R2, or either as referred to low secondary side or primary side it is I1 square R01, or secondary side it is I2 square R02, total loss. Okay, copper loss, that is denoted by copper loss. Okay, W copper. Okay, now how we minimize this? Why use a high grade copper conductor or aluminum winding conductor? Okay, winding. Okay, then second is iron or core losses. Now that is again categorized as a hysteresis and eddy current. Eddy current loss. Okay, hysteresis, it is due to BH loop, due to non-linearity of BH curve, like a reversal of magnetizing and demagnetizing of curve. Because in AC, at a 50 Hertz frequency, your magnetic core, transformer core are magnetized, demagnetized, magnetized, demagnetized. So there is an associated hysteresis loss. It appears as a heat. Eddy current are I square R loss because your EMF is also induced in the core material. Then due to core resistance, there is a losses. Now core is sort of to reduce this, we provide a laminated core. Core is laminated core, core laminated. Here to reduce it, we use a high grade copper, like your CRGO, cold rolled grain oriented silicon steel. Okay, or soft iron core, soft iron SS core, and this is called as a constant loss. Yeah, the constant loss. Why? Because they are constant. They not depends on not depends on load. But these are depends on load. This is called copper losses are variable loss. These are variable. Okay. Why these are variable? Because suppose this is your loss, copper loss. This I2 is load current. Suppose your load, kilowatt load on transformer. This kilowatt load, to convert into watt, you multiply by 1000. So what is the load current? Load current, we calculate load current equals to your kilowatt divided by V2 cos phi 2. Okay. Okay, dear. Means if kilowatt, now suppose your kilowatt load is increased. If load is increased, your load current is increased. If kilowatt load is decreased, your load current is decreased. Now suppose load is double, then this current is double, I2 dash. Then you know copper loss will be square time of this current. So suppose if double the load, your copper loss become 4 times. If current is double. If load is half, then your copper loss become 1/4. So at 1/4 load, your copper loss become 1/16 time, square time. Okay, dear. So this is called vary, because your load is vary, means your copper loss are vary. That's why they are called variable loss. So this question was in associated with same type. Here, it given here. Here are what are the losses, mention the various factors that affect the loss. So you have to discuss the losses and this. Now here, second B, there is a 25 kVA. kVA single phase 3300 by 233 volt transformer. Now we say that so that's why always we mention the load condition along with copper. So suppose you are at full load, your iron losses are given, that is 400 watt. No, sorry, iron losses are 350 watt, or we can write 0.35 kilowatt. Okay, and full load copper losses. Always we write the load condition along with copper loss because they are depends, no, loss are 400 watt. This load power factor, now he said that calculate the efficiency at half load 0.8 power factor. Now you write at half load and 0.8 power factor, lagging power factor. See, at half load and 0.8 power factor, what is the, you first write kilowatt output power of transformer is, what is the kilowatt output? So your KVA rating, rating into power factor, half of this rating at half load. My dear, 25 divided by 2 into 0.8. So what is the kilowatt at half load output? See, rating is the output, okay? At half load, it is half KVA rating means 12.5 into 0.8. It is 10 kilowatt, my dear, at half load. Then you calculate a total losses at half load. So you know iron loss. Now the iron loss are fixed at half load, full load same. But copper losses at half load. Half load. So at half load, this copper loss become, if you are 1/4, okay. So this is like 350 plus 1/4 into 400. So then it comes only 100. No, it is come 450 watt, or it is 0.45 kilowatt, no, losses. Then input power, if we calculate at half load, what is the input? Kilowatt input power to transformer equals to output at half load plus total losses, iron plus. So my dear, this output is 10 plus 0.45. It comes 10.45 kilowatt. Therefore, efficiency at half load. What is the kilowatt output at load? And then input into 100. Output is, input is 10.45. Percentage, not kilowatt.
Sir, copper loss 1/4 into 0.8.
या वही चीज तो यहाँ पर बताए थे ना हम, क्या क्या समझा रहे थे? Why this variable loss? हाफ लोड पे आपकी करंट क्या हो जाएगी? देखिए इस इक्वेशन में मैं ये 1000 V2 वोल्टेज तो आप चेंज नहीं कर रहे सेकेंडरी साइड में. सी दिस इज योर ट्रांसफॉर्मर, दिस इज लोड. तो यहाँ पर वोल्टेज, इसका पावर फैक्टर cos phi2 एंड V2 आर गिवन. जस्ट यू हाफ द लोड, हाफ मीन्स हाफ किलोवाट. तो जो आपका फुल, व्हाट इज द फुल लोड ऑन ट्रांसफार्मर? फुल लोड रेटिंग, भाई ये जो रेटिंग क्या है ट्रांसफार्मर? 25 kVA मीन्स एट फुल लोड इट गिव द 25 kVA into 0.8. What is the kilowatt at full load?
हेलो, फुल लोड किलोवाट क्या होगा पावर आउटपुट? 25 इंटू 0.8, 20 कितना आएगा फुल लोड पे? व्हाट इज द किलोवाट आउटपुट एट फुल लोड? देन हाफ लोड पे व्हाट इज द किलोवाट? 10 किलोवाट. इफ लोड इज हाफ, तो दोनों कंडीशन में जब फुल लोड है तो ये जो लॉस दिए थे कॉपर लॉस, इट इज एट फुल लोड माय डियर. ओके, ये फुल लोड पे, तो हाफ लोड पे क्या हो जाएंगे? Because your copper loss are depends on square time of load current. So you're at half load, your current is half, then your losses as compared to full load, this is now become square time na. So square means half current, it is half na, as compared to full load. Now load current become 1/2 times. Now square of this into R02. We can write na, this is copper loss, new copper loss. Okay.
Yes, yes, I understand. Thank you, sir.
If we can take na, if you are if load is double, so if load is double means your copper loss become four times. If your load is reduced to 1/4, then your copper loss become 1/16th time. Okay, it is a relation. This is your example. Okay, bye. Here. So tomorrow we will continue. Okay, this transformer chapter.
हेलो
Yeah,
सर, एक मिनट में स्क्रीनशॉट लेता हूँ.
just
सर ये वाला लास्ट का जो टॉपिक है सर लॉसेस वाला, ये शेयर कर दीजिए सर ग्रुप में विद न्यूमेरिकल सर. थैंक यू सर.
1300 रुपये चपला. 1300 रुपये चपला. काय बोला? होय. 1300 रुपयाचे घेते. यांची मोतीच्या वर्षी 1300 रुपयात बोला 800 रुपयाचे 1000 रुपयाची किंमत असते.
तसा नाही, आणि गावात आम्ही ते पेनू नाही शकत. किती 400 रुपये.
मग 1000 रुपये नाही होता. मग 1000 रुपये नाही होता.
मी 1300 रुपये दिली. मी 1300 रुपये. याची पण किंमत मी 400 दिलेली आहे ना, ती कसली काय समजे नाही. याची पण 400 दिलांचे. विचार दिला.
okay, dear.
दर विचारतात.